There's a mystery at the very heart of the universe. We don't know how old the cosmos is.
Understanding the age of the universe is fundamental to understanding the universe at all.
It's at the heart of everything.
It's more than just celebrating a birthday.
We want to know how much mass is in it, how much energy is in it, how it behaves. We have to have this number nailed down.
The age of the universe enables us to not only understand where we came from, but potentially the fate of the universe, what will happen millions and billions of years from now.
But our quest to discover the age of the universe is starting a war.
Usually nature just whispers to us. Now nature is screaming in our ear that we're doing something wrong, and that's exciting.
We think the universe started with a bang.
Everything that has ever existed is squashed up in the space smaller than a pinhead. And all of a sudden, space just starts expanding everywhere at once.
The idea that the universe grew from a ball smaller than a pinhead is hard to understand. But figuring out when it happened sounds like it should be more straightforward.
It seems like a simple question, right? But it turns out getting the age of the universe is pretty tricky.
Scientists have just a single fact as their starting point. The universe is expanding.
When people realized the universe was expanding, they thought they finally had a way to estimate the age of the universe. Take the universe now and run it backwards in time. Things get closer and closer till they come to a single point. That time to that point is the age of the universe.
The expansion rate is so important, it's been given its own name, the Hubble constant.
The Hubble constant is the present-day expansion rate of the universe. It is a key ingredient to understanding the entire expansion history of our universe and its age.
Scientists discovered a strange radio signal permeating the cosmos. It's the remnants of ancient light from the early universe. We call it the cosmic microwave background, or CMB for short.
The cosmic microwave background radiation is simply the afterglow of our Big Bang, the way the universe looked when it was 400,000 years old.
The European Space Agency launched the Planck satellite. Using sensitive radio receivers, the orbiter studied the sky in every direction, measuring tiny changes in the temperature and polarization of the radiation signal.
The CMB has all these variations in temperature, and they're not randomly generated. They are there because of physical processes that occurred when the universe was in its primordial fireball phase.
The red blobs are where matter was hottest, and the blue areas are where matter was cooler. The smallest red blobs are where hot material was packed tightly together.
That's where material in the universe would have been denser, and that's where galaxies would preferentially form.
It's so cool to get to look at those blueprints and study them and see how that baby universe later grew up into the universe we see around us today.
Although it doesn't look like much, hidden within this picture is almost everything we can know about the universe. In a complex process, using different mathematical models, cosmologists figured out how the ancient cosmos captured in the CMB became the universe we see today. They worked out how the universe got from small to big, and how fast that expansion happened.
The data from the cosmic microwave background is absolutely the gold standard for cosmology. It's beautifully clean, we can understand it really well, and we have a lot of confidence that what we learn from it is pretty robust.
By running the expansion backwards, we get an age. 13.82 billion years. Job finished. But it's not quite a slam dunk. The figure must be verified.
We don't make a single measurement using a single technique. We make multiple measurements via multiple techniques.
Another group of scientists use a totally different method to calculate the age of the cosmos. measuring objects that we can see in our universe to determine how far away they are and how fast they're moving away from us as the universe expands.
The most direct and most accurate measurements are using what is known as parallax. Parallax is the apparent shift in an object relative to the background when it's viewed from two different locations.
So if I look at my thumb with one eye, and then I close it and look at the other eye, it looks like my thumb moves.
If I move my thumb closer to my face, then the distance it moves back and forth changes. It appears to move back and forth more.
That parallax difference as we move the thumb closer and farther from the face is the way we measure distances to distant objects.
Using parallax, we can measure the distance to bright stars called Cepheids in the Milky Way.
Cepheids are stars that burn 100,000 times brighter than our sun. So they're extremely bright and they pulsate, meaning they get brighter and dimmer over a regular time period.
Cepheids that pulsate at the same rate have the same brightness. They're known as a standard candle.
A standard candle is something that is a standard, meaning we know how intrinsically bright it is. So all we have to do is measure the brightness that we appear to perceive on Earth, and then you solve for the distance.
So imagine that you're on this street. By looking down the street, you'll see that the street lights get dimmer and dimmer the farther away they are. But that's not their intrinsic brightness. Their intrinsic brightness is the same. So by seeing how faint the farthest away ones are, you can understand how far away they are from you.
We can use standard candles to measure the distance to stars farther away. But there's a big problem. Throughout the universe, there's a competition between the expansion, pushing things apart, and gravity, pulling things together. In the Milky Way, there's so much matter that gravity wins. Even looking at galaxies in our neighborhood, the expansion is tiny. But at cosmic scales of very different galaxies, matter is more spread out and expansion wins. So we can only measure expansion over massive distances.
The way we start to measure distances to things that are farther and farther away is to use something we call the distance ladder.
Each category of object that we observe is on a separate rung of this ladder. Measuring the distance to one will then inform us how far away the second rung is, and then the third rung. So each rung depends on the previous rung. And from stacking these together, we can start to measure things very, very far away from us.
Using parallax to measure Cepheid stars in the Milky Way gives us a benchmark. We can then use their standard brightness to measure Cepheids in other galaxies. The next rung is a brighter standard candle called Type 1a supernovas. They can be seen in galaxies farther away. Finally, we can measure light from distant elliptical galaxies. And by looking at how red the light is, we can work out how fast they're moving away from us.
So those three things give us the nearby universe, the somewhat far away universe, and the very distant universe, rung by rung.
March 2021. Scientists measure the light from 63 giant elliptical galaxies, the farthest rung of the distance ladder. They hope to get the most accurate measurement of the Hubble constant to date and a precise age for the universe.
The light that comes out of an object can get shifted if it's moving. If an object is moving away from us, then those wavelengths will get stretched out down into the reds.
So, as the universe expands, distant galaxies look redder than expected. It's known as redshift.
Redshift is very similar to the Doppler effect. That's something a lot of us are familiar with. That's where you have a siren. If something's moving away from us, we'll hear its pitch drop. Or if we have a car that's moving towards us with a siren, the pitch will go higher.
The team used the red shift of the elliptical galaxies to work out the age of the universe. Their calculations make the universe 13.3 billion years old. not too far away from the figure of 13.82 billion years given by the cosmic microwave background, a difference of around 6%.
That sounds trivial, but that equates to hundreds of millions of years of cosmic history that either happened or didn't happen.
50 years ago, when we weren't quite as good at measuring everything about the universe, we would have been thrilled to have our numbers agreeing to this level. But nowadays, having a difference like this, it's unacceptable.
Clearly, the two techniques do not agree. Cosmologists split into two camps.
We had hoped that these two methods were like building a bridge from either side and then meeting in the middle, but they're not.
Now we know that something is going on we don't understand.
Even though these measurements are roughly the same, it's really dangerous to just accept them and assume that everything's fine. Because in science, usually the initial really big discoveries start off as small differences that then you pull on that thread and something wonderful emerges.
So, does a simple question, how old is the universe, unravel everything? The universe is expanding outwards. The rate it's growing is called the Hubble constant, and it's the key to working out the age of the universe.
So the Hubble constant might just seem like some, academic number that doesn't mean anything, but that number contains information about the composition, the evolution, and the fate of the universe.
It's an important number, but there's a problem. Our best measurement methods don't match.
It's incredibly frustrating to not know how old the universe is. It's even more frustrating to know that there's two experiments, which are excellent experiments that we firmly believe in, that completely disagree with each other.
My hair fell out a long time ago over this kind of stuff. This has been the #1 question for over half a decade.
There must be something wrong with one of the methods.
There's a definite sense in the community that whichever camp you happen to fall into, the problems lie on the other side of the fence. So if you're mainly working with the cosmic microwave background, you probably think something is up with the distance ladder.
If there's a problem with the distance ladder, there's a prime suspect. The ladder relies on stars that have a predictable brightness called standard candles.
But there's evidence that these stars are not always the same brightness. So if you expect an object to have a particular brightness and it has a different brightness, then whatever conclusion you draw that relies on the brightness of that object is going to be off somewhat.
Think of the stars like streetlights. If one light is broken and dimmer than the others, you might think it's farther away.
The concern with a distance ladder is that if any of the single rungs is not perfect, then the entire ladder might be out of whack by the time you get to the top.
What we need is a fresh approach to measuring the age of the universe.
We're hoping we could bring in a tiebreaker, a referee, a brand new method that didn't care about any of this or any of that, and tell us what is the Hubble constant.
We may have just found one. This observatory doesn't have a telescope. It's hunting for an invisible wave, a disturbance in space-time itself, caused by massive objects accelerating or colliding. It's known as LIGO.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory, and it is a ground-based gravitational wave detector.
A perfectly stabilized beam of laser light bounces in a 5-mile-long L-shaped tunnel. As a gravitational wave passes through the detector, space stretches, forcing the light to travel a tiny bit farther.
You're bouncing a laser over an incredible distance and trying to measure as space-time itself gets stretched and deformed, whether that laser had to travel a tiny bit further or a tiny bit shorter. And a tiny bit here is the width of a single atom over miles and miles of distance.
LIGO has already detected colliding black holes, but it's also received a signal from something less massive.
Neutron stars are the densest thing in the universe other than black holes. They're the last stopping point before you would collapse all the way to form a black hole.
They're the size of Washington, D.C., but they can have the mass of 2 suns. A collision between neutron stars is incredibly powerful.
It's one of the most energetic events in the universe, and it distorts the fabric of space-time very strongly because their gravity is so strong.
But unlike black hole mergers, neutron star collisions can also send out light. In 2017, LIGO sent out an alert. More than 70 telescopes on Earth and in space swung into action.
This binary neutron star merger was the first time we'd witnessed gravitational waves and light waves coming from the same event. It was groundbreaking.
This event is ideal for Hubble constant hunters. The light tells us how fast the colliding stars are moving away from us. Gravitational waves give us the distance.
If we know how far away it is and how fast it's moving, that's the Hubble constant.
Having neutron star mergers added to your arsenal of ways of measuring the universe's expansion is great because it's completely independent. It uses physics that's not related to either of the 2 competing methods we have so far.
Sounds perfect. The result?
So this brand new measurement that we're hoping would be a tiebreaker ended up coming right in between these 2 extremes. Thanks for the help.
But it might not be as bad as it sounds. The number of neutron star collisions where we've detected gravitational waves and light? 1.
We shouldn't be at all disheartened by the fact that this hasn't actually decided the problem, because there's a huge margin for error when you have just one object.
We would like something like 100 events like this neutron star merger. That might seem like a huge improvement we need, but actually it's very feasible that in the next decade we'll get there.
Gravitational waves may give us a precise age of the universe, but there is a chance they'll tell us the problem isn't with our measurements, but with our understanding of the cosmos.
If we keep getting different answers for the Hubble constant, especially depending on the method we use, that's a big clue that we don't understand something fundamental about the universe's evolution, its makeup, something important.
Our search for the age of the universe just might destroy our model of how we think the cosmos works, plunging physics into chaos. We don't know the age of the universe. We had hoped that the results from our experiments would be like building a bridge, starting at opposite ends and meeting in the middle.
As time goes on, as the evidence accumulates, these 2 sides of the bridge are not going to meet. Something has to give.
Some believe the problem lies in the way we've interpreted the picture of the early universe, the pattern hidden in the cosmic microwave background.
We're really confident in the data that we have from the CMB, but it's actually an indirect measurement of the universe's age. It depends on our model of the universe being right.
It could very well be that our fundamental cosmological model that we've used to successfully describe the universe is coming up short, that there's something wrong in there, that engine is broken.
That engine is the standard cosmological model. Based on our knowledge of particle physics and general relativity, it's like an instruction manual for how the universe works. Rewriting it is a radical suggestion. For the most part, it matches what we see. But it does struggle with one thing.
As the universe expands away from the Big Bang, the intuitive thing you would expect is for gravity to start pulling it back together again. So over time, gravity would just reverse that and pull everything back in, back to a single point.
But what we see in the data is completely opposite. What we see is that the universe is not only continuing to expand, but it's speeding up faster and faster all the time.
To explain this weird phenomenon, the cosmological model relies on the existence of a strange, unknown force, dark energy.
Dark energy is the most perplexing and mysterious thing I've encountered in my research.
Dark energy is a term that we slap on this idea that the universal expansion is accelerating. That's about all we know about it. We don't know what's causing it, we don't know how it behaves, we don't know what it was like in the past or what it's like in the future. So we just call it dark energy.
It's invisible. It fills the whole universe and pushes galaxies apart.
In some sense, it's like a spring, a contracted spring, and you let it go and it wants to push everything away.
And things get stranger. Dark energy doesn't dilute as the universe expands.
As empty space gets created or expands, the dark energy associated with that stays the same. It basically populates all this empty space.
Imagine I'm draining a bucket of water and water just magically appears out of nowhere. That's like how dark energy behaves as the universe is expanding.
Because dark energy increases as the universe spreads out, it makes up more and more of the total energy in our cosmos as time goes on.
At the early phases of the universe, the first 5 billion years or so, the positively gravitating stuff like matter, dark matter, and light dominated the dark energy. But in the second half of the universe, for the last 7 to 8 billion years, the expansion rate of the universe has been ever increasing, so we say the universe is now dark energy dominated.
According to the Standard Model, it now represents 68% of all the energy in the universe. Dark energy plays an important role in the standard cosmological model. If our understanding of it is wrong, then so too is the model, which means the age of the universe we get from the CMB is wrong too.
Since nobody has a clue what dark energy is, there are a lot of different theories. But the biggest question of all is simply, is it constant?
Our standard assumption about dark energy is that it's pushing apart the universe with the same strength throughout the history of the universe.
Now, physicists are wondering if that idea is wrong. Maybe, in the early universe, dark energy acted differently.
Hey, you know the whole dark energy thing that's messing with the universe today? Maybe it messed with the universe back then.
It could be that dark energy really has affected the rate of expansion a lot more than we thought. This is going to throw a big monkey wrench into our idea of how old the universe is and what it was like at different eras.
The theory is called New Early Dark Energy.
So the idea behind new early dark energy is that dark energy was present during the very early periods of the universe, but in a very different state. Just like you can think of water being present in two states. It can be liquid water if the environment is quite hot, or it can be frozen water if the environment is colder.
We call that a phase change. Maybe in the early universe, dark energy underwent a phase change as well. It was different before then and acts differently now.
According to the theory, this more energetic state of early dark energy pushed apart the early universe much faster than we thought.
So that speeds things up in the opening moments of our universe, which starts to actually bring things back into agreement when you look at interpreting both the cosmic microwave background and the distance ladder measurements.
One of the things that we see in the universe is that things change with time. Density changes, matter changes, energy changes. Why not dark energy?
Adding new early dark energy to the early universe changes the Standard Model. The CMB gives a higher figure for the expansion of the universe. And finally, an age that matches the one given by the distance ladder method.
If you think about that bridge analogy, where the two parts just don't meet, the early dark energy adjusts the angle of the early universe part of the bridge, and it just gets them to actually meet in the middle.
It's still controversial, but new dark energy may be detected in detailed measurements of the cosmic microwave background.
I mean, in one sense, like, oh, do we really need to overcomplicate the universe here? But you know what? The universe is under no obligation to be simple.
But there's one thing physicists can agree on.
Dark energy truly is a can of worms we've just opened, and there may be some big changes coming up.
There is a more radical possibility. Maybe we need to ditch dark energy altogether and question one of the most famous theories of all, general relativity. Is it possible? Did Einstein make a colossal mistake? In trying to work out the age of the universe, physicists have started a revolution. A revolution that could overturn everything we thought we knew about how the universe works, including the bedrock of modern physics, Einstein's theory of gravity, general relativity.
Underlying everything, all of cosmology, is general relativity. But maybe we need a completely new understanding of gravity.
Gravity is a strange force. It's always attractive. The Earth pulling on us gives us our weight. The force of gravity acts over huge distances. The Sun tugs on objects throughout the solar system. The Milky Way pulls on other galaxies.
On the one hand, gravity is incredibly familiar to us, you know, the apple falling from the tree and all of that stuff. And we also know that gravity behaves in a very predictable way throughout our solar system, from all the spacecraft and things we've sent out. But when it comes to how it behaves on incredibly tiny scales, and also on incredibly large scales covering the whole universe, it's possible that we just don't yet have the right picture of what's going on.
Einstein's model of gravity has remained largely the same for 100 years.
So much of modern physics is really standing on Einstein's shoulders. But at the same time, we can't ever take anything for granted.
Claudia de Ram works on a theory called massive gravity. It's based on a key part of Einstein's theory that says gravity doesn't have mass.
Once you understand that general relativity is the theory of a massless particle, the immediate response should be, well, what if it was massive?
The theoretical particle that carries gravity is called the graviton. If gravitons don't have any weight, then there's nothing to slow them down as they speed through the universe. They can act over infinite distances, just like photons of light.
So one galaxy on this side of the universe can actually pull on a galaxy that's right on the other side of the universe.
But if gravity has weight, things change.
In some sense, we attach a little backpack to our graviton particle. Its effect is to slowly slow it down just enough so as to make its effect on very large distances being a tiny little bit weaker. And that's our way to switch off the effect of gravity on huge cosmological distances.
If gravity is a little bit weaker, a galaxy on this side of the universe can't pull on one on the other side of the cosmos. It has a huge effect on the expansion of the universe.
If the force of gravity actually just switches off at large distances, then you no longer have to counter the fact that everything's pulling everything else together, because it isn't anymore. So that would quite naturally explain why the expansion of our universe would be speeding up.
This acceleration is what we see in the universe today. Currently, we use dark energy to explain it.
So if the graviton has mass, that means that we can get out of the universe what we see without the need for dark energy.
What if actually what we were observing is simply the first sign of gravity switching off at very large distances? Maybe we're just observing the first effect of the graviton having a mass.
Without dark energy to deal with, the universe is a lot easier to explain.
Maybe we don't need these complicated physics. Maybe it's just all the normal ingredients of the universe, but operating under a different set of rules.
Claudia hopes her theory will soon be put to the test. Around 2037, we'll have a new gravitational wave detector, the Laser Interferometer Space Antenna, or LISA. It'll be bigger than LIGO and will orbit the Earth.
When LISA get out there in space, we'll even have a bigger handle on gravitational waves evolving throughout the whole universe. And so it will allow us to go very deep in our understanding of gravity.
LISA is a system of 3 satellites arranged in a giant triangular formation, 1.5 million miles apart. It should pick up very low-frequency gravitational waves from more ancient events, perhaps even shock waves from the birth of the universe. If the graviton has mass, then the waves will arrive more slowly than predicted. But until we receive those signals, all bets are off.
It's a big deal to propose a difference in gravity, but then again, we don't know.
I'm making no bets. The universe has proven itself to be so deceptive. So I'm gonna wait until it tells me what it is.
The question of the age of the universe opens Pandora's box. And the expansion rate of the universe holds another secret. Our ultimate fate, how the universe will end. We know exactly how the Earth will end. In around 5.4 billion years, the Sun will turn into a red giant, expanding to 1,000 times its current size. The Earth will be destroyed. Humans, if we still exist, will have long deserted our home planet. But how will the universe end?
The age of the universe enables us to not only understand where we came from, but potentially the fate of the universe, what will happen millions and billions of years from now.
If scientists confirm the value of the Hubble constant, the elusive figure that tells us just how fast the universe is expanding, it will tell us the age of the universe, and it will help us predict its end.
Measuring the Hubble constant is measuring the expansion rate today, right now. It's like checking your speedometer at one moment. But just because it's your speed now, it doesn't mean it was the same speed when you left your home or the same speed when you'll be on the freeway.
How the expansion changes over time will control the fate of the cosmos.
So depending on the Hubble constant, the universe could continue to expand, it could accelerate its expansion rate, or it could be decelerating.
At the moment, galaxies are racing apart. A continually expanding universe will cool down as it spreads out.
Another name for this eternal expansion is the Big Freeze, because as everything gets spread out, the density's lower, and there's no more opportunities for temperature differences. Everything just gets colder and colder and colder and colder, slowly, eternally approaching absolute zero.
The more matter is spread out, the less chance there is for star formation.
And so the universe's continued expansion means our night sky and every night sky in the universe will inevitably continue to get darker and darker and darker as things move further away and as stars die off.
Eventually, all the stars will go out, and there'll just be the leftovers, which we call the degenerates. Black holes, white dwarfs, rogue planets. It's gonna be a very, very sad place.
The last refuge of any matter at all will be black holes.
You've got a big black hole in the middle of each galaxy. Over trillions of years, everything in galaxies fall in. So finally you're left with big black holes over vast distances, separated almost universes away.
So getting towards the big freeze, black holes themselves start to evaporate. There won't even be black holes at the end of this accelerating universe.
All that's left is very, very low energy photons and a little bit of matter dispersed throughout the universe, and there's nothing left. That's it.
We call that the heat death of the universe. There's no longer any place that has more energy or more heat. It's all just thin, barely there photons.
It's fascinating scientifically, but from a human standpoint, not a lot of fun to think about.
But if the Hubble constant, the expansion rate of the universe, keeps increasing, then the end of the universe could be a lot scarier. and come a lot sooner.
One possibility is that the expansion of the universe will accelerate and continue to accelerate forever, faster and faster and faster. And if that happens, we face a scenario that we call the Big Rip, where actually the whole of space essentially just gets ripped to shreds.
So the solar system is going to get ripped apart. Then the sun and the planets themselves will start to get ripped apart. And finally, it works its way down to atoms. And atoms gets ripped apart. And we're starting to see effects on space and time. Space is ripped apart, time comes to a stop.
So in this scenario, time and space have no meaning. If everything is infinitely far apart, then space doesn't really exist. It's sort of beyond our comprehension.
Working out the expansion rate will tell us which scenario we face. But for now, the lifespan of the universe is unknown. Maybe we need to investigate the other end of the timeline. But how can we get a fix on the age of the universe without understanding its origin?
As you go back in time towards the Big Bang, our knowledge of physics really goes out the window.
Temperatures off the scale, pressure off the scale. The way everything behaved is just so different that the rules we have now do not apply.
The biggest problem of all, what came just before the Big Bang? Einstein's general relativity predicts that all the matter and energy in the universe was concentrated down to a single point, a singularity.
The singularity is like the part of those old maps that says, "Here be dragons."
Singularities are a problem. We don't like them. This is where basically you have a finite amount of matter in the universe, but it's squeezed down into zero volume, so it would be infinitely dense.
Infinite densities don't actually happen in nature. This is a sign that our math is breaking down. This is a sign that we need to replace that with a new understanding.
Many now believe Einstein was wrong. There was no singularity, begging the question, could the age of the universe be infinite? Scientists investigating the age of the universe are struggling to understand its origins. Could that be because there was no beginning? Could the universe be infinite?
Because we think we live and we die, we project that onto the universe. But that may not be the case.
The idea of an infinite universe is no more strange than the idea of a singularity. And in fact, throughout most of history, astronomers thought that the universe was probably infinite.
The foundation of our mathematical understanding of the universe, Einstein's general relativity, has a problem. It doesn't translate to the world of the very tiny, which is why its laws break down close to the Big Bang.
General relativity does a great job at describing things on scales that you and I are familiar with, and things like how planets move and how galaxies evolve, all the big stuff. Quantum mechanics, on the other hand, describes the world of the very small, the world of the atoms. The problem is that these two theories don't fit well together at all.
A new theory, known as loop quantum gravity, brings quantum theory and relativity together, and it makes a stunning prediction.
So one possibility is that the end of the universe could kind of match onto the beginning of a new universe and create a cycle of universes, one after the other.
Nicknamed the Big Bounce, it predicts a universe that stops expanding and switches into reverse.
And the idea here is that the universe can expand for a time, stop expanding, and then begin to contract again. And some have suggested that perhaps there's a cycle of expanding and compressing. It bounces back over again.
One of the appeals of the bouncing model is that it allows us to get beyond the singularity.
A bit like recycling on Earth. All the components get crushed down and then reused, giving the cosmos no beginning and no end.
If the universe is cyclic, does the age even have a meaning?
Age is a construct of humanity because we need to count time. But if the universe is infinite, maybe it doesn't matter in the big scheme of things.
A contracting and expanding universe messes with the concept of age. But the very idea of an expanding universe provides another cosmic curveball. It might not be alone. It might be just one ageless universe among many. It's an idea embedded in the math of the Big Bang.
The most popular theory we have in astrophysics for what put the bang into our Big Bang is inflation. This idea that there was a kind of dark energy on steroids that made our universe double over and over, not every 7 billion years, but every split second, creating out of almost nothing a Big Bang.
When the universe was just 100th of a billionth of a trillionth of a trillionth of a second old, it underwent a period of rapid expansion called inflation. It doubled in size at least 90 times, going from the size of a subatomic particle to that of a golf ball.
The problem with this inflation is, but it doesn't really stop. It just makes this ever bigger space and says that, yeah, well, okay, there was one region of space where this crazy doubling stopped and galaxies formed, and that's us. But there's this vast realm out there where inflation is still happening.
In the spots where inflation stops, parallel universes form.
This eternal inflation means that new universes are popping into existence all the time, but they're completely separated one from the other.
We may be living in a parallel or pocket universe.
In science, the holy grail is to observe what you predict. So what we need now is a prediction of an observation that is a consequence of the existence of the pocket universes.
And some cosmologists believe they have one.
There are clever ways that cosmologists have cooked up to detect the existence of pocket universes. Ever so rare, another pocket universe may collide into our universe and leave an imprint in the cosmic microwave background radiation.
But until such a scar is found, many scientists remain unconvinced.
Many of my colleagues hate parallel universes. They just don't like the idea that our universe is so big and most of it is off limits for us. If you are willing to be a bit more humble and accept that the reality might be much, much bigger than we will ever see, then parallel universes feel pretty natural.
It's really interesting how everything in the universe is tied together. We can start with a simple question like, how old is the universe? And here we are questioning virtually everything about the universe.
Cosmology's century-long search for the age of the universe forces us to question our cosmological model, the nature of gravity, and even time itself.
The age of the universe does bring up sort of profound philosophical questions about how a universe can even start. How can you create something from nothing?
The vast majority of whatever the universe is eternally hidden to us. So we answer the questions, how big, how old? And those very answers show us that we don't even know if we've asked the right questions to begin with.